Hello, everyone, and a very warm welcome to Kognito Key. Today, we're diving right into the fascinating and honestly sometimes a little bit stubborn world of magnetic materials. We are going to unpack a fundamental concept that literally powers our modern world. We're talking about everything from the street transformers outside your house to the hard drive in your computer. So let's trace the loop and uncover the absolute mystery of magnetic hysteresis. Now, you might be wondering what exactly happens when you turn an electromagnet off, but it just doesn't quite listen to you. You flick the switch, the power completely stops, but that magnetic field just stubbornly hangs around. Why do these magnets kind of lag behind our commands? Well, to figure that out, we need to look deep inside the material itself. And that brings us straight to the star of our show, magnetic hysteresis. Now, this word actually comes from the Greek hysterein, which literally means to lag behind. And in physics, this occurs when the magnetic flux density, which we call B, actually lags behind the magnetizing electrical force, or H. So the magnetic effect is quite literally trailing right behind our electrical effort. So let's meet our main character here, the unmagnetized ferromagnetic material. Right before we apply any power to it, it is completely disorganized. It's like a giant puzzle where all the tiny magnetic dipoles inside are just pointing completely randomly. Up, down, left, right, you name it. And because they're all over the place, they basically cancel each other out, meaning we have zero overall magnetic field.
But what happens when we finally switch the power on? Okay, step 1, we increase the current to apply a magnetic field. Step 2, all those scattered dipoles suddenly snap right to attention, perfectly aligning in one single direction. As we keep pumping up that current, we hit step 3. We reach what's known as saturation point, At this exact point, the material simply cannot get any more magnetized. It is totally maxed out.
Now, here is where the mystery truly begins. Imagine we decrease that electrical current, bringing our magnetizing force all the way back down to 0. You'd naturally expect the magnetic flux to just drop to 0 too, right? Well, it doesn't. Instead, the flux density rests at a new, higher value on our axis, which we label as OB. So even with 0 current flowing, a surprisingly strong magnetic field still remains. We actually call this leftover power residual magnetism. It is represented by that precise OB segment. It's the flux that's retained even when the electrical force is completely gone. And a material's sheer ability to hold on to this magnetism is known as its retentivity. You can think of it as the material's memory. It literally remembers being magnetized. So what if we want to wipe that memory entirely clean? Well, we just shift our power switch into reverse. By sending the current in the exact opposite direction, we forcefully push that stubborn residual flux all the way down until it hits absolute 0. And that lands us exactly at point C. Now, the effort it actually takes to reach this point is what we call our coercive force. It is the precise amount of reverse electrical heavy lifting that's required to wipe out that residual magnetism and, well, coerce all those dipoles right out of their alignment. And if we keep on applying that reverse force, we push right past 0 and into negative saturation down at point D. Then, dropping the current back to 0 leaves us with negative residual magnetism at point E. To fix that, we apply a positive coercive force at point F. And finally, we just increase the positive current again until we close the entire loop, landing right back at our original saturation point, A. So there it is, our completed hysteresis loop. But here's the kicker. This shape isn't just some abstract mathematical map. The total area enclosed inside this entire cycle represents actual, real-world electrical energy that is wasted. It gets lost as heat. Basically, the wider this loop is, the more energy you are losing just trying to flip those magnetic dipoles back and forth. And understanding this loop is absolutely crucial because it dictates two completely distinct families of engineering materials. First, we have soft magnetic materials, like silicon steel. These guys have a really narrow loop, low coercivity, and minimal heat loss. But on the flip side, we have hard magnetic materials. These possess a very wide, stubborn loop. They hold onto their magnetism extremely tightly and demand a whole lot of energy just to demagnetize. So how do we actually harness this out in the real world? Well, we use hard materials for anything that needs permanent memory. Think about the magnetic stripe on your credit card or your computer's hard disk. We absolutely want high retentivity there. But for devices that have to constantly flip their magnetic fields, things like transformers and electromagnets, we desperately need to use soft materials. That's how we minimize energy loss and keep the whole system running super efficiently. Isn't it just amazing how a completely invisible lag dictates the technology we use every single day? Honestly, controlling that wasted energy is the big secret to modern electrical engineering. Now, if you found this journey as fascinating as I did, please do hit that like button, share this explainer with your friends, and make sure to subscribe to the Kognito Key channel for more incredible insights. Thank you so much for learning with me today, and I'll see you in the next explainer.